Good afternoon. Today we are taking the last part of the chapter 4, which was the first part was about the filtration, and we say that we have two types of filtration based on their performance. We have slow sand filter, we have rapid sand filters, and the filtration rate for this one is about less than 8 meter cube per day per meter square, and this is when we have above from 60 to 120, I think, meter cube per meter per square per day. And we say that we have backwash flow, and the backwash is used usually for rapid sand filters, and we want to how to wash the filter. So this is the back rate or back washing rate, which is equal to the Q over the area, and which Q, which is the backwash rate. Now, filtration rate is equal to Q required by the area of one filter, and backwash rate is the Q backwashing per one area of the filters. And we say we have the depths, and we have the equations for filtrations, and we have the troughs. And I think I posted to you two videos, and let me again, if you just for making more clear. Um, okay, now you can see this is the normal filter. Normal filter means by this is the troughs. You can see there is the trough here, and this part is the troughs. Yeah, you can see. And this is normally working. The water is coming inside the filters. So it's coming from this way. I don't know whether you can see it or not.
That's clear, Doctor.
Yeah. Now look at this one. Now what we have, this is the process of backwashing. The process of backwashing, sorry, the water is coming into the filters, and everything is working normally. You have under this, sorry, under these blue, these are the troughs ones. Under these, there is about 60 centimeters. So 1 meters are clean depth of water. Then there will be the filter media. And after what we have, the filter media, there will be regular sand and rock. Now we will push the water inside the filter. So the destination of the clean water is just to pass through the filter media and keep cleaning the water. Now the process, when it reversed, it means that it will come to be backwashed. I have to stop inflow of the water from this gate. There is a gate here. So what we have to do is to just stop that one and let the water is coming from the from the bottom, and you can see the water is now coming from up, and yeah, it's coming from up, and you can see. So yeah, so what will be happen? Now the water is coming from back, and it will come inside the troughs. This is the troughs, and you can see this is a process of cleaning the filter. These are all, these channels, small channels, are called troughs, and this is called gallery. So gallery of the gullet of the collection of the troughs inside, and this is usually it will be made from the galvanized iron plate, or it will not be concrete, by the way. Cut this one. Now it's normally, you have to stop for a while until, yeah, this is the input, and you got the input. The one gate is working for outlet and one is going to, yeah, this is a hole that's working for outlet, and you can just close that one and you have another one for inlet. Yeah, this is for the inlet. So this is for out, this is for inlet of the water. So they are working inversely. Either you have input or you have output. Yeah, this is the, sometimes we need to have air bubbles because the water inside the gravels are very, the mud is very attached to the media, and it make kind of gravel mud. And this is now the process of, first of all, we have to just inject air, and it will look like bubbling just to make the vibration between the filter media. Now it starts. Now look at this is all during backwashing. It's called the backwashing. So how much water is needed to have this backwashing? It depends on the Q that we have. This process should be done every 48 hours once. You have to wash your filter every 48. These are all the suspended materials that was in water, and it will be captured by the filter media, and it's now going out from the filter until you will get this process will be, we need air 10 minutes for air jetting, and then water, then air and water, and then we need at least half an hour just to settle down to the media to come back to its position. And after that we are working with the normal, this is the normal way that we are using water. Okay, is it clear now for you how this proportion is working? We have in Slimani, in Slimani water treatment plant, such kind of filters. And remember that the number of the filters and the flow are, we have an equation of that 1.22 times square root of Q. This is was the filter. And now this is the work, the filter is working. This is the inlet, and the water is going from the troughs, and then it will go out of the trough and it will come inside the filter, and the filtration process will start. Yeah, now it's working. Yeah, any question? Do you have any question? Hello? Okay.
No, doctor, thank you.
Okay, thank you. Now this was what we have regarding the first part of this chapter, and later we will have a second part, which is called disinfection or chlorination. And this was the filter, the inlet, and the filter media, and this is the design of. By the way, the troughs, the way that the troughs that used for collecting the water is having this shape, or sometimes this shape, or sometimes this shape. And it's not clear here. It's look like between them, both of them. So it's like parabolic rounded, like you say, what you said, you saw in the film. Now, how to design this one, how to design this shape or this channel, it means how much is the depth it will be, and the base of this channel, it will have an equation which is 1.73. The Q is the flow per one channel. What by channel means by trough. For example, if I want to see this one, look at this one. This is 1, 2, 1, 2, 3. We have 6 troughs. So when I want to design the flow for a section of this one, so I will just we have Q backwashing divided by 6 to get the flow in each trough. Why? Because the flow is coming from up, and it will be collected in one and those 6 troughs. So usually you have flow to divide by the number of the troughs. There is another thing. There will be the first. This trough should be the center of this trough, and the wall it should have 1 meter clean distance. And between one trough to another trough, we have 2 meters. So basically, if we have 1, 2, 3, so we have another 2, and we have another 1 meter. So what will be the total width of this tank? It will be 1 plus 2 plus 2 plus 1, which is equal to 6 meter. So 6 meter will be the length of this tank, of this filter. This means, now in this case, we have 1 meter, and then there will be another 2 meter, and there will another 2 meter, and there will be another 2 meter, and there will be 1 meter. So if we have 4, 1, 2, 3, 4, 4 troughs, means how much is the total length? How much it will be? Hello?
Sir, I have a question.
Yes.
Is the 2 like from the center to center, or is it between them?
Yeah, the 2 is center to center. And the center of the first one and the last one, from the center, it's center to the wall, it should be 1 meter. Okay? Now, 1 meter is from the wall, that's the first one. And from one to another center to center should be 2 meter. Now, it means that we have 1 plus 2, 3, plus 2, 5, plus 2, 7, plus 1, 8. So if I have 4 troughs, means I should have the total about 8 meter. So 8 meter is the width of the is the length of this filter, and we have it in this drawing. This is when we have the first. If we have 1 trough, this is a trough. If I have 1 trough, so it should be 1 meter from the wall. This is the wall. Well, this is the wall. So if I have 1 trough filter, so it means that this has become 2 meter. If I have 2 troughs, this is 1 trough. This is another trough. So the center to center from this trough to that trough is 2 meter. Plus we have 1 meter from that trough to the wall, and 1 meter from this to the wall. So the total means we have 4 meter, and so on. If I have 3, so the width should be 6, and then you can find the length. So this will be the width, and this will be the L. L should be fine due to and this is, by the way, we have some dimension. We are using this kind of tables in the design purposes. Now, I think we solved this example in the previous chapter, but we will also review it. We have the Q, and we have 12 rapid sand filters. So it means per 1 rapid sand filter, we will have 4,000 meter cube per day. This is when we are going to, we have to divide the total flow. This is the total flow, and we want to design for 1 filter. So we have 12 filters. So this flow should be divided by the 12 to get the flow per 1 filter. And after that, we have the filtration rate. The filtration rate is 160 meter per day. It means that we have a high rate. This is the filtration rate, and the definition of the filtration rate is the Q divided by area of 1 filter. So the Q of 1 filter divided by area of 1 filter. What is the Q for 1 filter? Is 4,000. And what is the area of the 1 filter? I am looking for that one, but I have this one. So the 4,000 4,000 meter cube per day divided by 160 meter per day will give you area of one filter. And to find the area of one filter, we have this area is equal to the length times the width. The width is depend on the number of the troughs. We have 2 troughs. It means that for 2 troughs, it means this will be trough 1, this will be trough 2. So that this center to center of these 2 troughs are 2 meters. Now from the trough and the wall is 1 meter, and there is another 1 meter. So the width overall will become 4 meters. So we have this one. I will find the corresponding length. And to find that this belongs to the trough. For the trough, and it will be better to consider this trough is as a square. Means that the y and the b are the same. When you are considering that, it will be easier for us to find the dimensions by using this equation. This equation, when you have a y and this b, so when we are going to say this is a square one, so I will consider the y is equal to b. So I will just use this one as a b, and I have the q for each filter. Then I backwashing filter, by the way, and then I can find we have one equation with one unknown, which is the b. I will find the value of b through this equation. And we discuss overall these all equations, but this was as a review. Today, I'm going to just talk about another process, or another, it could be the last process in the water treatment plant, and it's called water disinfection. Disinfection, it means that we have done with the all suspended and with the all solid matters in the water. So what's left? The left is the biological one, and the bacteria and the viruses, sometimes the microorganisms, the dissolved ones. So what should we do? We should disinfect the water. So that the word disinfection or disinfect, it will be used to kill bacteria and viruses and all pathogens. Pathogens are those microorganisms that are hurting us and our health. Usually, we say that 99% of the water will be now clean before for the process of sedimentation, flocculation, and coagulation and filtration. Now, the last 1% is very important to know where it will be. It will be by destroying, or let me say, killing the bacteria and the viruses and the microorganisms. This process will be done by adding specific disinfectants like chlorine. Chlorine used usually and normally for chlorination. So chlorine or chlorination is one of the processes that we are using for disinfection. Disinfection in general, when you say that disinfection, it means that you are using materials to kill and purifying organic water from organic pollution. As maybe you are using chlorination, so this is called the chlorination process. Maybe you are using ozone for this process, and this will become it's called ozonation. And maybe you are using another kind of gas called fluoridation. And sometimes we are using UV, ultraviolet, for disinfection. And this is, we have different methods for disinfection. But the most common ones and the most effective one is called chlorination. Chlorine as a gas or as a solid materials used for purifying the water. Usually the water we have HOCl. This is called natural alkalinity. Water in general is naturally alkaline, and natural alkaline Then adding chlorine to the water, this is CO2, this is gas, will come with having this hypochlorite. This is called hypochlorite, hypochloric acid, which is not hypochloric acid, by the way, this is like this. It's not a stable gas. It will become ions and hydrogens. Now, this compound is the one that's acting on killing the bacteria, OCL. And usually we have this kind of in the detergents that we are using it in the houses. Usually it will be like NaOCl, and this compound is called the one in the white box, the white bottles, fast or something they are called flash or mu'jiza, or this is the NaOCl. And some of this is when you are using chlorine gas. Some of them are those OCl and HOCl. They are called free available chlorine. What means the free available chlorine? It will stay in the water free, and it will attack any kind of organisms, microorganisms that we have. Okay. The main property of this compounds are they have a short life cycle. It means that within 30 minutes, then they will kill all the bacteria and they will be dissolved. Now, within 30 minutes, the contact time between the viruses and the chlorine, it will be enough to kill the bacteria. This is the naturally when we have ammonia, there will be monochloride and dichloride. This is when we are adding more chlorine. There will be the results of adding more. This is the result of adding more chlorine. Now, how much should we add as an engineer? Why we need to know this one? Because one of the main buildings and one of the main properties of the water treatment plants, and which usually we face it, is how much is the dimensions of the chlorination tank or the chlorine that we need. First of all, to calculate how much is the doses that we need, usually the chlorine is used to kill bacteria. It means there's bacteria and we need to know how much is the demand for killing bacteria. So if I have 10 milligram per liter, it was the dose that I am adding to water. First of all, you have to say how much is the needed dose for killing bacteria, plus that I will add some residual. The some residual, it means the free available. Free available chlorine, it means that sometimes you need this meter cube of water that you are sending from Dukan to Slemania. You are purifying the water in its source. Now, from Dukan to Slemania, there is more than 50 kilometers. Now, any sudden pollution or any sudden impaction of the water inside, you should have like antibodies. So you should have a dose. It's called residual chlorine. This will be free available for in any sudden pollution. Now, I have, let me share this with you. The process of chlorination, how much we need to know how much is the added chlorine should be. First of all, in the lab, I will add, will be the chlorine dose. How much is the chlorine dose that we will add? I will add, so this is 0, this is 1. So the starting will be here. I will add 1 milligram per liter, and I will look for the residuals. You can see there is no residual in the beginning because the all added chlorine to this samples now, it's not working, not dissolving yet now. After that, I will add 2, I will add 3, I will add 4, I will add more than 5. So what will happen? The chlorine in the samples will be added and it will be accumulated. Since we don't have the chlorine are still not dissolved. Now after that, and when we have bacteria, this chlorine is surrounding this bacteria, and there's not any attack between from the chlorine to the bacteria. Just the process of surrounding the all bacteria and the microorganisms. Now, what will happen after a certain times, which is now we have the chlorine dissolved. We need about, this is about 30 minutes. Now, after 30 minutes, the process will be changed. The attack will start. Those chlorine attacking the micron. What will happen? The all available chlorine in the samples, now they decreased. They are all attacking to each other, so the number of the chlorine will be decreased. When it will be finished, when the bottle is finished, so we don't have any bacteria, and still I'm adding chlorine, then adding any other dosage from the chlorine, it means there is no bacteria, there is no any war in this one. So how much you add the addition of the dosage stay in the water. Now, look at this curve. This is a spoon curve. What we have here, this point is called break-even point. Break point is the point that is needed. It means that, for example, in this case, we have to add 7 milligram per liter. Why we have to add 7 milligram per liter? Because there was demand. This is the demand. This water is containing bacteria, and to kill the bacteria, we need at least at least to add one. We have to add 1 milligram per liter. This is the combined residual. The free residual, it will be above that one. So usually we have a dose or the chlorine dose that's required. It will be for demand to kill bacteria plus how much the free dosage that we need. For example, let's say that if the water is tested and found it, a test, this one, water is tested and found to have a chlorine demand. Means that this was for the chlorine demand was for what? For killing bacteria. So the demand means we need 1.9 milligram per liter. 1.9 milligram chlorine was required to kill the bacteria in 1 liter of water. Okay. Now, after that, we need, after killing the bacteria, we need to have a residual. This sample of water, this liter of water, should have at least about 0.8. So 0.8 milligram per liter is needed to be free available in any certain case. So the total demand is demand, or the total dose for adding chlorine will be, this is 1.9 milligram per liter. This is just a demand for killing the bacteria, plus how much is the required to be free available, 0.8. So it means that we have 2.7 milligram to 1 liter. Now for each 1 liter of the raw water, we need to have 2.7 milligram of chlorine. Now, if I have 1,000 meter cube, if the Q was 1,000 meter cube per hour, so how much is the total chlorine demand dose that we need? It will be Q times C. We have to multiply that 1,000 meter cube per hour times 2.7. By the way, milligram per liter, it's equal to gram per meter cube. It's the same. So 2.7 gram per meter cube. And there will be 2.7 times 10 to the power 3 gram per hour, or it is equal to 2.7 kilogram per 1 hour is the total we have to supply to this flow. So we have to look at this 2.7. Is it for 1 hour we need to have 2.7, and for 1 day it means that 2.7 times 24 hours. This will be the amount of kilograms that's needed per. It's about 0.7 times 24 hour. So it's about 64.8 kilogram per a day is needed. Now, do we have how to store this quantity of chlorine in the water treatment plant? In water treatment plant, what usually the chlorine will be added like this. This is bottles of chlorine bottles, and its weight about 1,800 kilogram. Yeah, it's 1,800 kilogram. It will weight, so the bottle, the weight of the empty bottle, chlorine bottle is equal to 800 and it's equal to 900 kilograms, and the weight of the chlorine gas is about 1,100. The total capacity is about 1,900, and the total capacity should be 1,000, twice the capacity of this tank. 900 is for the chlorine gas, kilogram. So 900 kilogram is the weight of chlorine in the bottle. When I say the bottle, I mean by chlorine bottle. Now, we said we need about 64.8 kilogram CO2 per day. So it means one bottle will be enough for how many days? We just 900 kilograms and divided by 64.8 kilogram per day. So it will tell us that 90
around 14 days. 14.
64, yeah, 0.8. It will be 13. 0.8 means between 40 days. So for 1 month, we have to provide 2 bottles, right? So we need at least to have one bottle, 2 bottles for 1 month for that 1,000. If the water was 1,000 meter cube per hour, this is the Q. Now think about this Q. This is one for Slemania. We have the treatment plant is 12,000 meter cube per day. So it means that we need at least for 1,000 we need 2 bottles per month. So 12 times 2. At least we have 24 bottles of chlorine gas per month. This is and by the way, you have to think about the price of this chlorine, and also usually as a good manager, and the government should at least have the for 3 months store, 3 months expectation of. So you have to have a storehouse for chlorine gas for 3 months. 3 times 24, it's about 72 bottles. 72 bottles we need to have as a store for that treatment plant. And think about the weight of each bottle. The weight of each bottle, it's about 2 tons. 2 tons means that you have to have a crane. It's called a frame crane, or Here's the crane. Yeah, we should have a crane. This is the crane, and this crane will be used just to lift, and this kind of we should have to, we should not roll in it because the chlorine gas is very, very explosive and it's toxic. Okay, now you can see there is how we are controlling the dose. When I say that we need 1.9 demand plus 0.8 residual, so how much is the total demand? Is 2.7 milligram per liter. How should we control this dosage to water? Usually there will be a device like this. This is called metering gas or metering chlorine to, this is just for metering the chlorine. You have a flow meter. This is the flow meter, and we just connect this device with the this cylinder, chlorine cylinder, and we should have, by the way, two parallel device metering. They should be two because, and look at this one and look at this one. In case that was stopped, then empty, just you have to release because this is what should be continuous 24 hours. So in case that one of them are empty, now we just close that valve and open this and exchange rapidly, very quickly with the other filled cylinder. This is the process of of chlorination. Do you have any question about this? Hello?
No, doctor, thank you.
Okay, any other? So we said that we have chlorine. Okay, thank you. So we have chlorine, we have ozone, and the most we are using it is chlorine. By the way, some of the treatment lab is not using chlorine gas. They are using hypochlorite. Hypochlorite is the chlorine in solid state, not in a gas state. So what you should do, we should prepare, we should dissolve it. Look at this one, dangerous. We will bring the dust one and we will dissolve in that one in this reactor, and then send in the chlorine that we will have into water. So there is a clean water, and look at the pipes. All the pipes and all the valves should be plastic one because the chlorine is very corrosive. We don't have it's a risk to have an iron gas, an iron pipes. Now, so this is another how to. This is the flow meter, the gas flow meter, the chlorine gas flow meters, and just link it to the volt. Some of the peoples are using iodine and barium. Are also there are other products that halogens, barium are also they could be used as a chlorinator, as a disinfector, but phenols, alcohols, soaps, and detergents, several acids, they are all used as a disinfection. I have just to tell you that this is I told you, and look at this example. What should be the chlorinator setting in pound per day? So we have either it will be milligram per liter of chloride. So the chlorinator we will set it as this one, or they use it as a pound per day. So the required is how much should be the added dose or chlorine dose. The chlorine dose, well, we say that the demand plus the free residual. So if I have the flow, the demand is 3.1 and the residual is 0.8, so the total is how much? will be 3.9 milligram per liter. We have the Q, which is equal to 2.46 mgt. mgt, oh, this is belongs to million gallon per a day. So what should I do? We should multiply that by this. So the dose is equal to 2.46. This is million to make it as a gallon. So it will be 2.6. This is gallon per day times how much that the total dose we have 3.9 milligram or gram per meter cube. So what should I do? I should just convert this meter cube is equal to 1 meter cube is equal to 1,000 liter, and just convert the grams to pound. So what we should do, 1 kilogram is equal to 2.5 pound, and then find in pound per day is the total dose that's required. This was one of my questions in the final exam in one of the previous semesters. Yes.
Excuse me, can you please repeat the final part of the previous example? The Q?
The Q. This one?
Yes.
Just, excuse me, just please. You asked about this part, question 2.
Yes, about the Q. How did we change
the Q? Yeah, how to change the million gallon per day? We said that we have two things. First of all, the total dose, chlorine dose, is equal to demand. Demand chlorine plus free chlorine. The demand is what is needed for killing the bacteria. The free chlorine, by the way, the free chlorine, we shouldn't have more than 0.8. It should be less than, because this is, by the way, the chlorine gas is a laxative gas, and when toxic when it will be more than, as a free chlorine, when it will be more than 5 milligram, it will be very toxic. So we should keep it less than 0.8. So in this question, we have 3.1 is the demand to kill bacteria, plus they ask us to have at least 0.8. So the total is we have 3.9 milligram per liter. And we say this unit, milligram per liter, is just equal to gram per meter cube, the same. So the chlorine required to be added is 3.9 gram per meter cube or milligram per liter. This is one. The second thing that we have is the Q. We have the Q for this is equal to 2.46 mgt. M belongs to million, G belongs to gallon, D belongs to day. So it looks like 2.46 million. I will convert million to 10 to the power 6 gallon per day. Now, how to convert this gallon per day? Because I want to see how much is the total demand, the dose. I will just multiply this Q by C to get 2.4 times 10 to the power 6 gallon per day. I should multiply it by 3.9 gram per meter cube. So look at this one. Look at this one. I will convert gallon with this meter cube. So just we have 1 meter cube is equal to 10 to the power 3 liter. So the meter cube with the meter cubes, it will be cancel out the liter with the, and by the way, yeah, this is liter. And what should I do? I will convert the liter with the gallon. We said that liter and the gallon. So 1 gallon is equal to 3.785 liter, right? Am I right?
Yes, sir.
Yes, sir.
So gallon with the gallon will be also cancelled out, the liter with the liter. So what should I have? It's equal to 2.4 times 10 to the power 6 times 3.9 times 1 over 10 to the power 3 and times 3.785, and it's gram per day. Am I right? So 10 to the power 3, this is will be 3. So the result is equal to 2.4 times 1000 times 3.9 times 3.785. So the result is how much? 35,000 427.6 gram per day. Means how many kilograms? 35 kilograms, 0.42 kilogram per day. Am I right?
Yes, doctor.
Now, what is required? Required is to find this value, but in terms of pound per day, not a kilogram per day. So in pound per day, so 35.42 kilogram per day. When I want to convert it to pound, so 1 kilogram is about 2.54 pound. Am I right? So this is will become like this. So 35.42 times 2.54 will becomes 89.96 pound per day. This is the total needed of the chlorine dose for a day. And now it's clear?
Thank you very much, doctor. Appreciate it.
Yeah.
Yes, sir.
Okay. Now this was another question, and I want to just show you what I have bring it to my students in the previous semester. This was the question. It said that the following data was obtained in a chlorination experiment. So we did a chlorination experiment. We have a sample and we added chlorine and we checked for the residual chlorine. First of all, I added the dosage that we add. It was 1. So what should I have to draw using this this diagram? I should say chlorine dose. It was 1. This was 1. Sorry. One, 2, 3, 4, 5, 6, 7. So when I added 0.1, the residual chlorine was exactly like this. So if this is 1, 2, 3, 4. So for the first one, and I added 1, the residual was 0.8. Look at this one, 0.8. In adding 2, The residual was 1.5. Where is 1 point? This is 1.5. It will be here. When we add 2.5, this is 2, this is 2.5, so the residual was 1.9. This is 1.9. And when we add 3, this is 3, when the residual is 1.25. So what will happen, or what happened? 1.25, this curve is coming down. When we have 3.5, this is 3.5, the residual is 0.5, and this is 0.5. And when we add 4, this is 4, then it will become 0.65. It increased slightly. And when we have 4.5, this is 4.5, it become more increased, but it's still below 1. And in the 5, we have 1.9. This is 1.9. And it will be better if you made a very good. So look at this one. If I want to draw, this will be the curve. Usually this should be linear, by the way. So you have to draw in between. And by the way, this question, it will be solved by hand or by using hand drawing. Look at this one. You have to stop here. You will draw a line here and you will extend this line this way. You have to extend this line here, and you have to extend this line here. And this line is the best. This is a line, and this should be a line. So what will be here is the point, the intersection point. It's called break point, BP. B, it's the break point. Break point will give you exactly what you add, what you have to add. So what will be the break-even point? It will say that will be the total demand. So the break point is to be, you have to conflate to, it will be 3.5, 3.6. It will be 3.6 milligram per liter. So 3.6 milligram per liter is needed just to completely kill the bacteria, and after that we have to having about 0.5 combined chlorine. So just look, what we have in the graph. Look at this one. What I did here is so the break point will give you a point. This is the point. It will be how much is the chlorine dose that's required to kill the bacteria, and to make a combined residual for about this much. And what will be above that, it will be free residual. So for example, if I am looking, if I said I have added 8 milligram per liter, so 8 milligram per liter means having about 1 milligram for combined residual, and this will be free residual, is the free available chlorine in this tank. And yeah, this was the my question in the final. I think it was in the final exam. So yeah, the question was said, find, I think here's the guy, plot the data. I plotted the data, and found the break-even point. This is one. Then find what dose is required to provide a free residual of 0.7. So the second part of this question, I want to have free residual 0.7. So what will be 0.7? You have to measure free residual. It means that After this point, you have to measure about 0.7. Where is the 0.7? We have about, this is 0.6, 0.5, 0.5, and to have free residual of 0.7, so it means 1.2. So you have to find 1, this is 1, 1.2, 1.4. This is will be the total needed dose, means 4.8 milligram per liter chlorine is needed just to have 0.5 combined and 0.7 free. Yes, please, sorry.
Yeah, I just wanted to ask that we add both the 3.6 plus the 1.2 to get the total needed, but you just said.
Okay, so we added both of them. If I have just added only 3.6, then the free residual will be 0. But this is only for break-even point. You need more, yes, so you should add points. You need how much free available? 0.7, so you should add more chlorine. And how much it will be more chlorine? You have to find this one from the curve. 0.5, adding that beyond the break-even point, you have to look after that dosage. So 3.6 will give you 0 free available chlorine. 4.8 will give you 0.7 free available chlorine. Is it clear?
Yes, sir.
Now,